Hello, welcome to our first video lecture for Chapter 2. So this is video lecture 2.1, where we begin our study of motion along a straight line. So let me go to my first slide. Chapter 2, motion along a straight line. Let me start by pointing out that there is content that you can read from our textbook. Our textbook is a digital textbook on a website known as Wiley Plus, because the publisher's name is Wiley. The title of the textbook itself is Fundamentals of Physics, 11th edition. In these video lectures, I summarize the material that you can read from the book. But I strongly urge you to read the material from the book because there's a lot more detail and a lot of example problems there. So let me show you what that material looks like on the Wiley Plus site. Now, I've already sent you a separate document with information about how to obtain access to the Wiley Plus site. That is where you are buying access to our textbook. And when you purchase that access to our textbook and log in to the Wiley Plus site, to read our textbook, this is the home page that you will see. Okay? It says Wiley Plus. The first name of the first author that you will see, that person's last name is Halliday. The title of the book is Fundamentals of Physics. It is the 11th edition of the book. This is the home page that you will see. And you see a menu along the top. And you see one of the buttons is Read, Study, and Practice. So if you click on that, you will get a screen that lists, I'll click on this little button first, another menu with a drop-down list of all the chapters in the book, and you want to choose or select Chapter 2, Motion Along a Straight Line. And then you will see chapter resources, reading content, and section 2.1 is hyperlinked, position, displacement, and average velocity. And if you click on that, wait just a moment, you will get the actual reading content from chapter 2, section 1, position, displacement, and average velocity. And then you read. You just start reading. And I strongly encourage you to read this content. Read every word of it. You'll love it. It is clearly written, very accessible, and one of the things that makes our textbook unique amongst all the physics textbooks on the market is that it has embedded a little assessment questions. You can try them. They don't count for anything point-wise, grade-wise. They're just for you to practice. Okay? And they're meant to help you assess if you're understanding the reading as you go along. So it poses a little question. You enter an answer, you scroll down and there's a button, check answer, and you can click on that to see if your answer is right. And if you don't want to do all that, you can just click on this button that says Show Solution. And when you click on that, a little mini window will appear when you're reading it online. It doesn't show up in this video, but it will when you're reading online, and it will show you the solution to that question. And you can go through all the reading. There are a number of embedded questions. Okay. There are a list of learning objectives and a summary of key ideas that you just read, and then more applications by means of example problems with embedded questions as you go. Okay. So when I refer to reading in the text at the beginning of a video lecture, this is what I'm referring to. I strongly encourage you, if your time permits, to read this content because my video lectures are merely summarizing what is in the reading. And now I'm going back to my summary of the reading, and I am summarizing Chapter 2, Section 1, position, displacement, and average velocity. Okay, so let's begin. With this chapter, we begin a 3-chapter sequence on what is called kinematics. In kinematics, we are describing the motion of an object without addressing without addressing what's causing that motion. We'll save the study of the cause of a motion for later on. Now we're just going to describe how a particle is moving with descriptive words. But more than just words, also mathematics. Quantitative description is what we mean. This is science, after all. And science is precise and specific. And in physics, when we describe motion, we use math. Lots of math. So when I say describing the motion, I mean something more than, oh, look, there's an object and it's moving around. Isn't that pretty? Okay? So you'll see as we start bringing in all kinds of very specific terms how we're going to describe the motion of an object. We're also going to limit ourselves to the motion of what we call particles. And by particle in physics and in kinematics specifically, we mean any object in which every part of that object moves in exactly the same way at any given instant. One of the things you'll come across if you do the reading in Wiley Plus for section 2.1 is a little animation that your author shows showing the motion of an armadillo moving along an x-axis. And the armadillo's motion is rigid. Every part of it is moving in exactly the same way along an x-axis. That's the kind of motion along a straight line of a particle that we're going to focus on in Chapter 2. If you want some other examples of things that are more realistic or more everyday, you don't often see an armadillo moving around, that we would put into this category, say a drag car, a drag race where cars move in a straight line, or an airplane on a runway during its takeoff roll, but before it starts to take off and leave the ground, then it's moving along the runway. You can think of that as motion along a straight line. And we'll see other examples. That's the kind of motion we're going to focus on in Chapter 2. So to describe that motion, what do we do? Well, we're going to define some very specific terms or quantities that we will use to help us describe the motion of a particle. So let's start looking at the various quantities that we're going to define. First quantity, position. Position is just a location or a coordinate on a chosen axis relative to a chosen origin. So here you see a depiction of part of an x-axis with a chosen origin, and we can have some particle. Maybe it's an armadillo, maybe it's an airplane on a runway, maybe it's a drag car on a raceway, whatever it might be. And it's going to be moving along on this x-axis. And at any given time, any given instant, it has a position. It is located somewhere on this axis that you see. And you'll notice that this x-axis has a scale of meters. You can see the m over there on the right by the x. That tells you that the numbers that you see on this x-axis, like the 1 or the 2 or the 3 or the -1 or the -2 or the -3, is an x position in meters. And then the symbols we use are x if the object's moving along an x-axis, or y if it's moving along a y-axis, or z if it's moving along a z-axis. In Chapter 2, we tend to use x for a horizontal axis, an axis that's along the ground or parallel to the ground. A vertical axis, we tend to use y. That's just kind of convention. But position is a coordinate that tells you where the particle is located at any given time. Now, if the object is just sitting on the x-axis and never moving, then its position is never changing. That's going to be pretty boring. We're not going to limit ourselves to just that. We're going to be more interested in particles that change their position on an axis, such as an x-axis. Right? They're moving around. So we need something more than just position, or at least it's useful to have something more than just position. The next quantity we're going to define is called displacement. And by definition, displacement is change in position. Note the emphasis on the word change. Now the SI unit of displacement is still meter, symbol for that unit m, but now the symbol for the displacement, let's say the particle is moving along an x-axis, is delta x. That's a Greek capital letter delta followed by an x, meaning change in position. Okay? Final position minus initial position for a given time interval that has to be specified. And displacement is where we start to emphasize what we call vector quantities. And any vector quantity has both a magnitude and a direction associated with it. The magnitude of a vector quantity can never be negative. It's just the absolute value, if you like. And the direction, which is denoted by a sign, is, at least for our horizontal x-axis that you see up above, either the positive direction of x, to the right, or the negative direction, to the left. And so if a displacement delta x is a positive quantity for a given time interval, what that's telling you is that the particle ended up to the right of where it started. If the displacement delta x for a particle is a negative quantity, that's telling you that the particle ended up to the left of where it started. So displacement allows us to keep track of how much the position has changed in a given time interval. Now let's go to our next quantity that we find useful to define when we're studying or describing the motion of a particle. And that next quantity is defined to be average velocity. Now we're starting to expand our horizons a bit. Not only do we want to keep track of how much a position has changed, but how rapidly has that position changed. That is often a useful thing when you're describing the motion of a particle. And so average velocity is the rate of change of position over a finite time interval. Or to say it another way, it's the displacement in a given time interval divided by that time interval. What is the SI unit of average velocity? Well, it's the unit of displacement divided by the unit of time interval, so meter per second. What are the symbols that we use in this book for average velocity? I'm going to focus for motion along an x-axis. The symbol is v with a subscript AVG, average velocity. It is defined to be, three lines here mean this is the definition, displacement over time interval, delta x divided by delta t. And then you see another way to express that, at least used in this chapter, x2 minus x1 over t2 minus t1. So we're talking about a finite time interval that begins at the time called t1, where the particle had position x1, and ends at the time called t2, when the particle had position x2. And with those definitions, the average velocity is computed by taking x2 minus x1 in the numerator and t2 minus t1 in the denominator. Average velocity, like displacement, is a vector quantity with a magnitude and a direction. And its direction is the same as the direction of the displacement of the particle for the given time interval, because displacement is right there in the numerator in the definition of average velocity. Okay, so what I want to turn to now is some a little animation to have us visualize the motion of a particle and get some practice with these ideas of position, displacement, and average velocity. So now I'm going to transition back to Wiley+. And I'm going to click on a different tab here in my browser to a simulation or animation that I have already opened. It is on Wiley+. You can find it on Wiley+. Horizontal motion of a bead on a smooth wire. And it's going to represent a bead moving along an x-axis, where the x-axis is a smooth wire, and the bead has been threaded onto this wire and can move on this smooth wire. And something, we don't care what right now, is causing it to move. And we're going to run an animation. It's going to start at time 0, t equals 0, and it's going to end at the time chosen by this slider labeled t stop, which right now is 1 second. So when I run the animation, it's going to run for 1 second. It shows the bead as a red disk on the x-axis. You can see that it's currently located. Its current position is x equals 2 meters. Let's run the animation for this 1 second time interval and see what we observe. Okay, in this time interval delta t, between t equals 0 and t equals 1 second, the x position changed from x equals 2 meters to x equals 4 meters. So, what was its displacement, delta x? Pause the video and answer that for yourself. Okay, did you pause it? Did you think about the answer to my question? What is the displacement of this particle, this bead, on this 1 second time interval? What is delta x? And did you say that delta x is positive 2 meters? Because you take x final minus x initial, x at the end of the time interval, minus x at the beginning. X at the end is 4 meters. X at the beginning was 2 meters. 4 minus 2 is 2. So delta x is 2 meters, positive 2 meters, for this time interval. There's even a little blue arrow pointing to the right here to show you that the displacement was to the right or in the positive x direction for this time interval. Now let me reset, and with this little drop-down menu, I can change when t-stop is. I'm going to change it now to 3 seconds. So now the time interval is going to start at t equals 0 and end at t equals 3. Let's observe the motion. Okay, so that was a 3-second interval. Here's a question for you again. What is the displacement of the particle for that interval? Again, pause the video, think about it for a moment, get an answer, and then come back. Okay, welcome back. Did you say that the displacement delta x for the time interval I just showed you is 0? Delta x equals 0 for this time interval because x initial was 2 meters and x final was 2 meters. And even though you saw it move, its displacement for this time interval is 0. So here comes another question for you to ponder. Is displacement, symbol delta x, as we've defined it here, the same thing conceptually as the distance a particle travels? Think about that. Pause the video, think about it, and come back. Okay, welcome back. So, generally speaking, is displacement for a particle and distance traveled, are they the same concept? Answer, no, not necessarily. Distance traveled is just the ground covered in a time interval. So if I can slide this slider back and run it again, I can see that it travels to the right a distance a little more than 2 meters because it goes from x equals 2 to x equals 4. And then it travels back that same distance to get back where it started. So the distance traveled is a little more than 4 meters, but the displacement is 0. Okay, so you got to be careful and always think of the definitions of things. If we ask you for displacement, don't give us distance traveled. Because in physics, these words that we're defining to describe motion in kinematics have very specific definitions and meanings, and we have to adhere to those. All right, let me reset the animation. Now let me change the stopping time to t equals 5 seconds. Okay? I'm going to run the animation. Let's watch again. Okay, now there quite a bit happened in this 5-second time interval. Okay? Here's the first question for you. What is the displacement delta x for that interval? Pause, answer, and come back. Okay, welcome back. Did you say the displacement for this time interval, delta x, is negative 10 meters? The negative sign is important. The particle ends up to the left of where it started. And the value is negative 10. because x final here you can see is -8 meters, and x initial was 2, and delta x is computed by taking x final minus x initial. Using algebra correctly, -8 minus 2 equals -10 meters. By the way, you also have to include the unit, m, for meter. Otherwise, the answer is incomplete. So the displacement here is -10 meters. All right, you ready for another little challenge? Calculate the average velocity for this time interval. Again, pause, think about it, and then come back. Okay, did you get that the average velocity for this time interval, v, avg, is equal to -2 meter per second? Why is that the answer? The definition of v average is displacement over time interval, delta x over delta t. So that's how we must compute it. The delta x for this time interval, the displacement we just said, is -10 meters. What's the delta t for this time interval? Well, t final is 5 seconds, t initial is 0 seconds, so delta t